Okay, folks. So today we're going to start a new chapter. We're now moving away from a classical description of metals using the Drude model, which treats the electrons as point particles that collide ballistically with the lattice ions every so often. And we're moving now towards a more realistic model of the electrons inside of matter, namely, they are waves. Quantum mechanics tells us that. And we've already seen how, in a particular specific model, the energies of these wave-like electrons came in allowed energy bands. So that's sort of where we're heading today. We want to start looking anew at energy bands for electrons in a periodic lattice. So we already know what the free electron looks like. So a free electron is a wave, right? And the energy of that wave is given by this parabola as a function of k. So we have an exact formula. E is equal to h bar squared k squared over 2m, right? And so that is parabolic. So here's our parabola. And then I've also sketched in particular values of k that are significant. So for instance, pi over a. We already know that that is a significant wave number because that's the number where in the Kronig-Penney model, we started developing a band gap, right? And the reason that this is a specific or an important k number, wave number, is that we get reflections from the lattice planes. So here, the criterion for reflections is satisfied. The Bragg condition is satisfied at pi over a, at minus pi over a, at 2 pi over a, and at minus 2 pi over a, basically any multiple of pi over a. All right. So now we're going to remember something that we've already derived on a homework assignment having to do with the Bloch theorem. So just to review that, we have that the Bloch theorem tells us that the wave function in a periodic lattice has to have this form, right? Psi of x has to be some part u of x times some other part e to the I kx. So this u of x, though, is periodic, exactly periodic in space with the periodicity of the lattice. But then you also get this phase factor. And so another way of stating that is that, sort of more compactly, is that the wave function, whatever it is, has to satisfy this property, namely that whatever the value of the wave function is at x, then at x plus a, the value has to be the same as it had at position x, but with the addition of a phase factor e to the I k a. Right, so x and x plus a sort of have similar values for the wave function, but they differ by this phase factor e to the I k a. Now k here is any real number. So for k equals 0, we said, for instance, for that particular state of k equals 0, then we can say that the wave function is identical at x and at x plus a. All right, but for other k values, that will not be the case. We can summarize this equation by saying that if I move over by a lattice constant, I pick up an additional phase factor of e to the I k a. And so that almost becomes a definitional statement for k. Okay, so this property of the wave function defines what we mean by the wave number k, in a sense, right? It becomes the defining feature of k. in what it does to the wave function when you move over by a lattice constant. All right, so let's then we said look at another wave number, call it k star, and that k star differs from the original k by 2 pi over a. Okay, so that's the only difference. I've added another constant here, a constant offset, 2 pi over a. Okay, and then let's look at what this k star does to the wave function when I shift it over by a lattice constant a, right? So, well, we plug in k star next, okay, and then we distribute the a in the exponent, and we get this form here, and then we realize that the second factor is just 1, okay? That's another complicated way of writing the number 1, and so I really just end up with that. And notice that this here is not a k star, it is a k, all right? And so we conclude, therefore, then that this wave function has that same translational property as it would have had if we had used k. So k star has the same translational property as k, and we say that from this point of view, then, those two wave numbers are equivalent. They're not the same, but they're equivalent in what they do to the wave function. So that's sort of the argument. Okay. So just to summarize then, with k star, I'm sorry, with k we get this, and with k star we get something very, very similar. Okay, and so we say that the two are really equivalent, or another way of saying that more generally is that all k values that differ by a multiple of 2 pi over a are equivalent from the perspective of the Bloch theorem. So it's not just those two particular k values, k star and k. It's, you know, it's any two wave vectors or wave numbers here in one dimension, wave numbers that differ by any multiple of 2 pi over a. It could be 4 pi over a, it could be 6 pi over a. Any multiple of 2 pi over a, we're going to call all of that entire set of k values that differ just by a multiple of 2 pi over a equivalent to one another. Okay, and so that now leads us, so this was sort of just the preamble, okay, the motivating ideas for us now to move into new terrain. Namely, we want to define a reduced zone scheme. So what that means, I want to go into next. So what is first the extended zone scheme? Okay, well, the extended zone scheme is what we already had. Okay, so we just draw this parabola. Okay, and it just keeps going on and on and on, to the left and to the right. And now what I'd like to do is I'd like to sort of section it a little bit. Okay, so I'm going to treat this section here. Let's just for a moment think of the positive k-axis. There is a section from 0 to pi over a, and then there's a section from pi over a to 2 pi over a. Then there's another section from 2 pi over a to 3 pi over a. Okay, so I'm sectioning it off. This is sort of a blue section here, a red section, a purple section. And now I'm going to remember that that all k values that differ by 2 pi over a are equivalent. So here, for instance, I'm going between pi over a to 2 pi over a. Well, I could shift that over by, to the left by 2 pi over a, and wouldn't really have changed very much at all, right? Because of that equivalence. So I shift by 2 pi over a on the k-axis. Doesn't really do anything. So that's what I'm going to do. I'm going to shift this section to the left by an amount 2 pi over a. Okay, so what happens then? Well, now it's over here. right? So let's do this again. It was over here. Now I'm shifting this over to the left. So here's pi over a, then I'm adding minus 2 pi over a, so that lands it over here at minus pi over a, right? And this other edge here, this 2 pi over a edge, well, after the shift, will land at a k of 0. And so I'm going to get this translation. Now the energies haven't changed. I've just changed the k, which I'm allowed to do, okay, from what we said before. And I'm going to keep going, right? So the purple section from before, it's still here. I'm going to also shift that over by 2 pi over a to the left. Okay, what happens then? Well, now it's over here. Okay, fine. So then I'm going to look at the left side of this parabola. So here I kind of have something here that I kind of could shift now to the right, perhaps, by 2 pi over a. So then this edge gets shifted over here, and this edge gets shifted to k equals 0. So when I do that, then okay, that appears, this piece of it then appears over down here. Okay, and so here's another piece that I'm going to shift by 2 pi over a to the right now. Where does it land? Well, it lands right here. And so this is what we call the reduced zone scheme. I'm shifting sections of the extended parabola above so that I can fit everything into the reduced zone. Okay, and the reduced zone is going just from minus pi over a to pi over a. Okay, so this here is what I will call the reduced zone, or we can also give it a name. It's often called the first Brillouin zone of the 1D lattice. Okay, so that's the idea, and that would be my reduced zone scheme. So I'm going to apply these shifts such that I cram everything into the interval minus pi over a to pi over a on the k axis without changing the energies. Okay, and so, all right, so again, so we have the reduced zone scheme. Here it is. Okay, now I'm gonna add, so this was the free electron. But now I want to add a small periodic potential. So the free electron feels no lattice at all. But what if we now introduce a weak periodic potential that goes along with the lattice? Well, then we said we're going to open up gaps, right, at these particular wave numbers. In this case, we're only at, we said we open up gaps at multiples of pi over a. That's the Bragg condition. But since we're in the reduced zone scheme, there's only two significant wave numbers now, and that is pi over a and minus pi over a. And so we're going to open up gaps, and we might also open up a gap at k equals 0, as we saw from the Kronig-Penney model. Okay, so with this addition of a weak periodic potential, instead of the black line for the free electron, I might get a modification like this. Okay, so I'm going to slightly distort the energies, and that distortion is most visible at these particular wave numbers, pi over a and minus pi over a. Okay, so then the next one might be here. The next one might be here and here. So instead of the black lines, I'm going to get the red lines. because I've added a perturbation, right? A periodic potential that the electrons see. Okay, so I get this particular picture. All right. So what's next? Okay, so now you see that we have these gaps, right? So there's a first gap here. There's also a gap here. There's a gap here. There's sort of two gaps at the zone boundaries, you could say. The first Brillouin zone boundary at pi over a and minus pi over a. There's also a gap here that opens up as well at k equals 0. Okay, and so the upshot here is we get these bands, right? So this here then I can say is my first band, separated by the first gap from the second band. Then there's a gap at k equals 0. And here's my third band, separated from the fourth band. And so what I then end up with is a different kind of scheme. Before in the extended zone scheme, I basically allowed all k values from minus infinity to infinity. A single parabola, right, that went as far to the right as you wanted and as far to the left as you wanted. And yes, I can put in the weak potential and open up gaps at periods, at integer multiples of pi over a. Because that was the original picture, the extended zone picture. I'm labeling it as before. But now in the reduced zone scheme, I have done something slightly different. I'm restricting k, okay, the wave number, to just run from minus pi over a to pi over a, namely the first Brillouin zone, the restricted zone. Okay, and where do all my other k values go? Well, they go into the different bands, right? So I now have to have a subscript n on here. So now it's an e sub n of k, where k is restricted, but then I allow n to take on any positive integer. And it basically simply indexes the band, or refers to what band you're in. Okay, am I in the first band, the second band, third band, fourth band, and so on. So instead of letting k go from minus infinity to infinity and just having one continuous band, now I'm going to say, well, I'm restricting k, but then splitting things up into different bands. So that basically is the main idea behind the reduced zone scheme. Now, one nice way of generating the reduced zone scheme is to actually start from the extended zone, where you allow k to run from over all real numbers, and then draw in parabolas at multiples of 2 pi over a. So that's what we want to do next. Okay, so we're going to draw a whole bunch of parabolas. Okay, here is my first parabola, centered at 0. And then I'm going to draw my second parabola, centered at 2 pi over a. And you guessed it, now I'm going to keep drawing parabolas. Third one goes at minus 2 pi over a. And then I would keep going. So 4 pi over a, minus 4 pi over a. 6 pi over a, minus 6 pi over a. And so I get a whole array of these parabolas on the k-axis. Okay, so what do I do with all these parabolas? Well, first, here's my reduced zone, right? The first Brillouin zone. And you see here that magically we get what we got before, through that. Before we arrived at sort of the same picture via their translations, right, of different sections of a single parabola. Now we're not doing that translation business. We're just basically looking at a whole bunch of different parabolas and how they sort of intersect my reduced zone, my first Brillouin zone. And I get the same picture, interestingly enough. Right, so here's my reduced zone or first Brillouin zone. And I get sort of a similar picture. This is the free electron assumption here. So now I'm going to do the same thing with a weakly periodic lattice, right? So how would that, so it's just the same picture now, but how would this picture get modified? Well, I have to open up the gaps here, right? So for instance, there's a gap here, there's a gap here, there's a gap at k equals 0 here, and so on. So let me flesh out this drawing a little bit more. Okay, I'm going to draw a couple more parabolas in. Okay, and I open up gaps wherever these parabolas intersect. Okay, wherever there's an intersection between any two parabolas, I'm going to have to open up a gap in the weakly periodic lattice. And so I get a picture like this. Well, this picture is called the periodic zone scheme, and it's yet a third way of visualizing energy bands for electrons. Can you guess which band is which? Here, we're going to just consider this wiggly line down here. It's a continuous line on the k-axis. I'm going to consider that to be our first band. And then here's my second band, okay? And then here's my third band. So this is another scheme, another way of sort of identifying bands. It's called the periodic zone scheme. So yes, we have these three schemes currently, and let's see where this is all is heading. Okay, so basically to summarize, this is our first band now. It's sort of this wavy line that extends over the entire k-axis. Okay, and then here on top we have the second band separated from the first band by this gap. But since we're not looking at the reduced zone, it also extends over all of k space. And then above that we have the third band, and so on and so forth. Okay, and so if we draw in what we define to be the reduced zone, here it is. Okay, and we get the reduced zone scheme back. Okay, so we just basically limit what we're going to look at. This goes on both to the right and to the left, but we limit our attention to this region between minus pi over a and pi over a on the k-axis, and we get our reduced scheme back. And so why can't we sort of ignore or throw away the rest of the periodic zone scheme and just focus in on the reduced zone scheme? Well, the answer is actually quite obvious, right? Because it just repeats. There's no new information. All the information is sort of contained in here, in this yellow shaded region. And then this is just a repeat of that, right? So from pi over a to 3 pi over a, we get exactly the same picture as we got from minus pi over a to pi over a. And the same thing over here, from minus 3 pi over a to minus pi over a. It's this exact same picture again. So there's really no new information over here or over here, and all the information is contained in the reduced zone scheme. So the periodic zone scheme isn't really all that useful. You see it though sometimes in textbooks, and that's why I mentioned it. In our textbook, for instance, it is referred to. And sometimes, so even though it doesn't really give you new information, it is sometimes still useful, as we'll see later, to consider that view. So it's not completely redundant to think about the periodic zone scheme, although, to be fair, there isn't any new information contained outside the reduced zone scheme. Okay, so just to summarize then, yeah, all the information is already contained in this region. So to summarize, we have 3 different ways of visualizing electronic states. We have the extended zone scheme. That's where we started out, right? So that is just a single parabola. And if you want to introduce a periodic potential, then you modify that, a single parabola, but it still just keeps going on, both to the left and to the right. Okay, and then we said, well, we can sort of fold everything back into the region, which we'll call the reduced zone, the region from minus pi to plus pi over a, minus pi over a to plus pi over a. We can fold everything outside of the region in using these shifts that were allowed from the Bloch theorem. Okay, and so everything that used to fall outside of that restricted zone, we can now fold in, okay, by shifting various sections of the parabola into that reduced zone, okay? And, you know, we're shifting some sections by 2 pi over a, others by minus 2 pi over a, by 4 pi over a, minus 4 pi over a, 6 pi over a, minus 6 pi over a, right? So we can shift by any multiple of 2 pi over a and have an equivalent Bloch wave number. And so now we're just shifting everything into the reduced zone, and that gives us the reduced zone scheme. Okay, and so once we have the reduced zone scheme, that can also repeat over and over on the k-axis, and that gives us then the periodic zone scheme. Right, so those are the 3 schemes we're gonna look at here in the next week or 2. Well, 2 weeks or 3 weeks actually. So thank you.